All right, let's take a look at today's lesson. We're going to be looking at partial fraction decomposition today. This is a pretty important concept for us actually in BC calculus. In BC calculus we do, in calculus 2, we do partial fraction decomposition. Calculus 1, calculus 2. Calculus 1 does not really do partial fractions, calculus 2 does. So AB calculus is just calculus 1, BC calculus is calculus 1 and calculus 2. Okay, so we really, in Cal 2, we do partial fractions. So let's look at what is involved. The very first thing that we're going to do is we're going to look at it's a rational equation. We're going to look at it and we're going to divide it if it's improper. That's the very first thing that we would do. And so what does that mean? So this n would be my polynomial in the numerator, d is my polynomial in the denominator. It's improper if the degree of n, the numerator, is bigger than or equal to the degree of d. So for example, if it were like 3x squared over, say, x squared plus 1, that would be improper because those degrees are equal. I think that's one that kind of sometimes gets biased. If they're equal, it is also improper. So we need to do long division. What we would do is we would do long division and then we would work on the remainder. The remainder would be what we would work on with our partial fraction decomposition. Think about the quiz that you just took, that long division. Remember how you had like the whole part plus, what was it, 4x minus 2 over something? Remember that? That's the part, the 4x minus 2, that you would do the partial fraction decomposition on. I don't have an example of that in the notes, but we do have examples of that in the daily work where you have to divide first. Okay? The second thing, once we have gotten it in its proper form, then we're going to factor the denominator completely into linear and irreducible quadratic factors. That's a vocabulary word, right? We've been working on that. We should know what that means. Linear and irreducible quadratic factors with real coefficients. All right, so let's talk about the difference between linear factors and quadratic factors and how we set up the partial fractions. So what our goal is, let's talk about the overall goal so you understand what we're doing. We're taking this big complex fraction, or this complicated, not necessarily complex, it's a complicated rational fraction, and we're going to split it into little bitty fractions. Why would we do that? Because it's easier to integrate little bitty fractions than it is a gigantic, massive fraction. That's the technique that we use. So we want to break it into little pieces. So that's our goal. So we take a big fraction, we break it into a lot of little fractions. That's why it's called a partial fraction. What we do is, let's say we're working on the denominator, let's say we get a linear factor. Let's say our factor is, I don't know, x plus 2. Okay, let's say we factor the denominator and we get x plus 2, x plus 3. I'll just make that up. Right, so that's, the bottom of one of our fractions. So the way that I would set up a linear factor is I would see how the linear factors all have just letters over them. So what I would do is I would set this up as a over x plus 2 plus b over x plus 3. I mean, that's how I would set up my partial fractions if there were linear factors. That's how I would set it up. Now let's stay on linear factors for just another moment. If it's a repeated linear factor, let's say we factor it and we get like, I don't know, x minus 5 squared. This is not an irreducible quadratic factor. Notice that the exponent of x is 1. That's linear. It's linear if the exponent of x is 1. Right? This is a repeated. It's x minus 5, x minus 5. That's two linear factors. X minus 5, x minus 5. It's repeated. What we do with repeated linear factors is we use this pattern right here to expand them out. So this would be equal to a over x minus 5. That would be like this first one right here. Plus b over x minus 5 squared. That's how we break apart repeated linear factors. We would follow this pattern. And if this were cubed, I would have another one, plus c over x minus 5 cubed. Okay, so that's how we deal with linear factors. They either look like this, or they're repeated and we have to expand them like that. Those are our choices. I'm just talking about expansion of the partial creating the partial fractions. There's a whole lot more to it in the notes on the next page. So let's deal with irreducible quadratic. What if we have a quadratic factor that's irreducible? Let's say, what if we factored and we got like, x squared plus 4? We should know at this point that that is an irreducible quadratic, because if I continue to factor, I would get imaginaries, wouldn't I? That's irreducible quadratic. So if that is my factor, then instead of putting just an a over it, I'm required to put this kind of notation over it. I'm required to put ax plus b over it. Okay, that's how I would expand that. Now let's say I have a repeated one. Let's say I have x squared plus 5, and that is cubed. Let's say I factor the denominator of my rational expression, and I get that. So how am I going to expand that? I'm going to use this pattern. So that would be ax plus b. Notice how I put something different in the numerator if it's an irreducible quadratic versus a linear. And that would be x squared plus 5 plus cx plus d over x squared plus 5 squared plus ex plus f over x squared plus 5 cubed. Okay, so on this first slide, we're just talking about the setup. What do we do? How do we expand it? How do we write the different partial fractions down? All right, so are we okay with the difference between a linear factor and a quadratic factor and how we treat them differently? Also, repeated ones are different. Okay? All right, so I have two examples on the other slide where the first one actually is kind of intense. I probably should have reversed the order of them. The first example is a pretty intense example. The second one is a bit easier. So let's just kind of go crazy. Let's start with the second one because it's a little bit easier, and then we'll go to the first one because the first one is pretty intense. All right, so not to alarm you, it's super fun. I mean, not to alarm you, but let's start with number 2. Okay, let's start with the second one. So we look at the second one. When we look at it, we have to determine, is it improper? No, I have a second degree on the numerator, a third degree on the denominator. It is not improper. I don't need to do long division. The second thing that I do is factor the denominator completely into linear and irreducible quadratics. So we take this, let's see, I have a GCF of x squared plus 4. Okay, so that is, I have one linear factor and one irreducible quadratic factor. Okay? Now, what we're going to do is we're going to expand it out. I'm going to take this fraction, set it equal to. I encourage you to do exactly what I'm doing. Take the fraction and make it equal to our partial fractions. So, my first one is linear. I would put a over x plus. My second one is quadratic. So I would put bx plus c over x squared plus 4. And I'm going to hold here for a second. Are we all okay with the expansion? Okay. Once we get it expanded, what we're going to do is we're going to multiply this whole equation, it's an equation, by the common denominator. That's what we're going to do. We're going to multiply the whole thing by x times x squared plus 4, over 1. We're going to multiply it all out. So let's do that. So I multiply this, I'm going to multiply it by each of the fractions. Okay, I multiply it times the first fraction, and I'm left with 2x squared minus x plus 4. Okay, because the denominators wipe each other out. I multiply it times the first expression, see how the x's cancel each other out, and I'm just left with a times x squared plus 4. I hope we can see that right. So I'm doing several steps at once. I'm multiplying and simplifying at the same time. Hopefully that's not too disturbing. All right, so now I'm going to multiply this times this last piece, and I'm going to get bx plus c times, and what's missing is x. So let's pause here for a second and make sure we're okay. So we expand the partial fractions, then we clear them. We multiply by the common denominator. Okay, which I know you've done before. I mean, it's a thing we've done before. All right, so at this point, what I'm going to do is I'm going to multiply this completely out. The a times each of those, the x. I'm going to multiply it completely out before I go to the next step. So I have 2x squared minus x plus 4 equals. So I have ax squared plus 4a plus bx squared plus c times x. Now I usually don't do that step, but when we first learn it, it's probably a good idea to multiply it all out. Or I'll show you a different technique in the other example that I'm getting ready to do. So what we're going to be doing now is actually something that we do on the SAT test or the PSAT test. It's a technique that they like to use. That's really, we don't use it very much in class. Maybe that's why they like to do it. But what we do is we basically make an equation with the coefficients of matching terms. So take a look on the left there. I have x squared on the left. I have x squared on the right. See the coefficients right there? The coefficient of the first x squared is 2. So I'm going to make an equation. What I'm going to do is make an equation and then solve the system of equations. Doesn't that sound fantastic? We get to solve system of equations. Yay! All right, so let's kind of underline. I'm going to underline all the x squared terms. So here's an x squared term, there's an x squared term, and there's an x squared term. Okay, so I'm going to make an equation with the coefficients of the x squareds. I don't use the x squareds, just the coefficients. So it's 2 equals a plus b. That's my first equation of my system of equations that I will be required to solve. Okay, what do you think would happen? This numerator doesn't have to have a 2x squared. What if it didn't have an x squared? Would this equation be gone? No? What would happen? Well, if there was an x squared over here, let's pretend this is not here. What would the coefficient of the x squared be? 0. So this would be 0 equals a plus b. It's still an equation. It just would have, this side would be 0. We just want to make sure we're clear on that. In the other example, I do have some zeros, so hopefully that'll make sense. All right, so now let's kind of line up all the just x's. There I have an x here and an x there. Okay, so I have that coefficient of that x is a -1. The coefficient of this x is a c. Okay? And then the last one, I want to line up the constants. So I have a constant here and a constant there. That, they don't have an x with it. So I have 4 equals 4a. And that's the system of equations that I have to solve. Usually it's fairly simple. Look, they already gave us what c was, right? And a really easy matter to find a. So I just need to back substitute to find b. So it's really usually not a really intense system to solve. It's usually, fairly easy. So a, I think we can see a is going to be 1. C is -1. And now let's work on b. So I would plug in. So 2 equals 1 plus b, so b is going to be, what, 1? Okay, so now I have my a, b, and c. My last step is to take these and put them in the partial fractions. And I'm done. So a was 1, so my first fraction is 1 over x plus. B is 1, so it's basically going to be 1x, which is x. And c is a -1, so x minus 1 over x squared plus 4. And that's my answer. Okay? So I started with one with not a whole lot going on. A little bit. Certainly we have a mixture of linear and quadratic factors. How are we on that one? Okay? Okay, now let's go to number 1. Now that hopefully you have like the concept under your belt, so you're like, okay, I kind of get what's going on. Let's go to number 1. So number 1 has a lot of stuff going on. It's actually already, well, first of all, the degree in the numerator is 2, the degree in the denominator is 4. It's not improper. We would not divide. It's already completely factored for us. I have one linear factor that's just a plain old linear factor, and I have a duplicated linear factor. It's duplicated 3 times. Okay? So let's split this out. Let's bring it out into its partial fraction. Let's decompose it. So my first one, I'll deal with the x. So it's a over x plus. Now we have to do the repeated factor thing. You know, that that technique that I was showing you. So the first one is going to be b over x minus 1 plus c over x minus 1, x minus 1 squared plus d over x minus 1 cubed. Okay? So I have expanded that out. Next step is we're going to multiply the whole thing by the common denominator by x times x minus 1 cubed. We're going to multiply the whole thing out. So when I do, here on the left, I get x squared plus 1 equals. The first fraction is going to be a times x minus 1 cubed plus, right? So when I multiply that out, the x's go away. B times, this fraction doesn't have the x factor, and it doesn't have two of those, plus c times, let's see, this one has an x minus 1, has two of them, so I need an x and one of the x minus 1s. And then d has all of the x minus 1s, but not the x. Okay, that's a bit more intense. That's a lot more algebra. I'm going to have to multiply all that out. Now I know we have FOILed before. I'm not going to take the time to FOIL each one independently. I'm just going to go to the answer. I hope you're okay with that. The x minus 1 cubed, I FOILed that out already. And so what do we get? We get, so let's just go to that. We get a times, when I multiply x minus 1 times x minus 1 times x minus 1, I get x cubed minus 3x squared plus 3x minus 1. That's what I get there. Plus b times. I'm going to have to FOIL the x minus 1 times x minus 1 and distribute an x. When I do that, I get x cubed minus 2x squared plus x plus c, I've got to distribute the x, so I get c times x squared minus x, and I get d times x. Okay. We still have, so I've got all the multiplication done. Some students might like to multiply the a times everything, the b times everything, the c times everything. That might be a good idea, like I did over here. Okay, I'm going to show you a different way, in case you just see a different way. Instead, what I'm going to do is I'm going to collect the coefficients of, I'm going to go after, so I'm going to look at the x cubes. I got an x cubed here and an x cubed there. So what I'm going to do is I'm going to go to straight to, so we have x squared plus 1 equals. So the coefficient of this x cubed is an a, the coefficient of this x cubed is a b, so I'm just going to write them like this, a plus b x cubed. That's another way to do it. You don't have to do it that way, but if that's confusing, you can just go and distribute all the a's, b's, and c's and then combine like we did on the other one. Okay, so now I'm going to collect the x squareds together. So here's an x squared, here's an x squared, there's an x squared. I have 3 x squareds. So let's collect their coefficients together. So this x squared has a negative 3a coefficient. This x squared has a negative 2b coefficient. This x squared has a c coefficient. Okay. So next, let's collect our x's together. I have a plano x here, a plano x, and plano. I have 4 plano x's. Let's collect their coefficients together. So this x has a 3a coefficient. This x has a 1b coefficient, or just b. This x has actually a negative c coefficient. So I'm going to fix that instead of plus. We'll make that negative c. And this one is plus d, x. Okay, let's see if we have any constants. In other words, things that don't have x attached to them. So let's see. Oh, there's one right there. And that's actually the only one. So we just have one constant, and it is negative 1 times a, or negative a. Okay. So now we're going to set up our system of equations. I kind of already have it started for us. This one is cubed. Do we have a coefficient, or we don't have an x cubed over here, so what would its coefficient be? It would be 0. So 0 equals a plus b. That's my first equation for my system. Now, what about the x squared coefficients? I do have an x squared on the left. It's 1 equals, and my x squared would be negative 3a minus 2b plus c. Okay, let's work on the plano x's. Do I have a plano x on the left side? No, so its coefficient would be 0 equals 3a plus b minus c plus d. And then the last one, the constant, I do have a constant over here. It's 1, and my constant is negative a. That's the system of equations that I need to solve. Again, it's not too bad. It's just back substitution. I already know a is going to be negative 1, right? If I put that in here, can't I find b pretty quickly? All right, b is going to be 1, and then you just continue back substituting and you'll get the others. For time's sake, I'm going to go straight to the others. C, let's see where we are. X. So C happens to be 0, and D happens to be 2. So let's finish this out by putting those numbers with their little fractions. So A is negative 1, so I have negative 1 over x plus B is 1, so I have 1 over x minus 1. C is 0, so that wipes out this fraction altogether. There is no C fraction anymore. And then D is 2, and that gives me x minus 1 cubed, and that's my answer. Okay, so you're probably glad that I started with the second one rather than the first one. That one's a little bit intense, but still not too bad. I'm hoping that you're getting the concept. Any questions?